Pleasure to welcome you all here today to the second annual Martha Evans Distinguished Lecture, which will be delivered by Professor Bonnie Dorr of the University of Florida. This lecture series was endowed by the students of Professor Emerita Martha Evans to honor her legacy and an appreciation for her many years of devoted teaching and mentorship. Professor Evans, who was honored last year by the Association for Computational Linguistics Lifetime Achievement Award, was a pivotal researcher in the development of the field of natural language processing and computational linguistics, specifically in the areas of computational lexicography and intelligent tutoring systems. But beyond her research accomplishments, she also was and is the devoted and beloved teacher and mentor of hundreds of students. Over 100 PhD students she graduated over her career. She was also an incredible colleague and builder of the overall research community, and a tireless builder of our own computer science department, being one of the first hires in this department when it was founded in 1971, and a tireless builder of this department ever since. Professor Bonnie Dorr is a professor of computer science at the University of Florida and senior research scientist at the Florida Institute for Human and Machine Cognition. She leads the Natural Language Processing Research Laboratory there, working on deep language understanding and semantics, large-scale multilingual processing and summarization, and in many different application areas, and I think we're going to be hearing some of that today. She's carried out seminal work in cross-language divergence detection, machine translation, paraphrasing, automated evaluation, and more. She is also specifically a pioneer in developing the new area of cyber NLP, which combines natural language processing, cybersecurity, social computing, AI, to address some of today's most pressing problems. She's an triple AI Fellow, an ACL Fellow, and an ACM Fellow, and has been a Sloan Fellow, an NSF Presidential Faculty Fellow, and President of the Association for Computational Linguistics, as well as serving on the executive councils of triple AI and the ACL. And I could go on, but let's hear from Professor Dorr. Thank you very much for coming.
Thank you very much for that introduction, Dr. Argamon, excuse me. And I just want to say that Martha Evans is an NLP legend, and it is truly an honor to be invited to be a speaker in this series, and I'm just incredibly excited to be here. So thank you for that. Okay, so a few more details about who I am. You already heard some of it, but my research does focus on human language technology. My official start date at the University of Florida was 1 year ago, January 1, 2022. My research spans many disciplines within and across and outside of computer science, including linguistics and social computing. And a couple of years ago, with colleagues in the international community, I coined the term cyber NLP that brings together these disciplines within AI and cybersecurity. And I also focus on core problems and solutions in AI and NLP. And most recently, I'm focusing on explainability. We'll talk a little bit about that today. So although deep learning has become the centerpiece of many AI and NLP solutions, explaining how or why deep learning systems come up with the answer they come up with is still somewhat of an unsolved problem. It's at the heart of my work. So I'm collaborating with UF colleagues on this topic, and in all problems that I work on, I adopt a human-centered approach, which I believe to be the future of AI systems, getting machines to adapt to ever-changing needs of end users instead of the other way around, okay? And then before UF, as was mentioned, I was at a place called IHMC, Institute for Human and Machine Cognition. Before that, on the CS faculty at University of Maryland, 24 years. I also was on rotation 3 years at DARPA, the Defense Advanced Research Projects Agency. Okay, so I want to start by showing some examples of what makes NLP so hard, natural language processing. I'll present two applications. The first one is machine translation, and the second one is in the realm of cyber NLP, as was just mentioned, and I'll define that. This is a Chinese translation example I've been tracking for over 10 years, starting back in 2012. And this human translation reveals that the story is about a high-speed train collision in China a few years back that involved a government cover-up of the cause of an accident and deficiencies in the official rescue efforts. The literal translation Everyone heart in can guess, some more is the control public opinion, more cause masses heart arise in arise suspicion. This shows how much information is not explicitly expressed in Chinese, presenting a major challenge to automatic machine translation. Now, purely statistical translation, and I'll refer to machine translation henceforth as MT, has done fairly well on formal documents, articles, and newspapers, but initially failed to translate informal language, such as the Chinese example I showed you, which was posted, was a social media post. So here we all know, can guess a bit, the more the control of the mass media, more suspicious mind. Okay, and that was in 2012. Part of the problem is Chinese doesn't express the subject of the sentence. So in this translation, you can't really tell who's controlling public opinion or that it's the people that are suspicious and so on. Now, my colleagues and I have demonstrated a combination of statistical techniques and linguistic principles or hybridization, doing things together, bringing linguistic principles together with statistical or machine learning or deep learning approaches yields something like what we would see today. Everyone can guess something in their hearts, and the more you control public opinion in this way, the more people are suspicious. And here we see the subject of suspicious, which is the people. You is used generically to refer to the government. And that's one example of an application for language processing that I've worked on to illustrate some of the challenges in processing informal language, particularly multilingually. And I'll focus on the second example for most of the rest of this talk, which is the application that spans cybersecurity and natural language processing. A couple of years ago, my colleagues and I did a thorough analysis of a range of different types of social engineering attacks, and we built an AI response system. And we've all experienced these social engineering attacks. Someone spoofs an authority figure, for example, the dean of the college. And so the idea is to cheat people out of money. I need gift cards for our campus visitors, or I need access to resources. I need account information to update our grant records. Those sorts of things. And then for this example, and I'll do this later when we come back to this example, these acronyms are SE for social engineer and PV for the potential victim. And in our analysis, we noticed that the SE's prompt generally has some form of explicit or implicit demand, or what we call the ask, which is not necessarily a question. Click here is an ask, for example. And there's generally a framing for the ask, the promise of a 20% discount in this case. And we've demonstrated that a combination of ask and framing coupled with structural information about the communication channel provides a springboard for producing an automated response that wastes the attacker's time. So that's sort of the idea, is that keep them from attacking other people, essentially. So the response here is representative of the use of sociolinguistic principles in our team-developed system. For example, based on the phrase check eligibility, the system says, good to know, how do I go about the process of checking eligibility? To waste time and stall for additional information gathering opportunities, the agent says things like, the website's not opening. Did you provide me the correct link? Is this the one? So why is this important? First, some definitions. Phishing is a technique that's generally achieved through mass dissemination of the same communication to trick potential victims into engaging in a way that compromises sensitive data. It turns out that about 3% of phishing emails are open, and of those open, there's only a 5% success rate. But now, what about spear phishing? So spear phishing is more targeted. It's at the individual level. And it requires research about potential victims. Social engineer does this. So here, the social engineer could pose as a trusted individual and engage in customized communications. And it turns out that 70% of these messages are open, and with a 50% success rate of those open. That's a pretty big deal. So my colleagues and I set out to determine whether linguistically informed representations could help to address this problem. So I'll return to that shortly. That's an example of a social engineering system I developed with colleagues at IHMC a couple of years ago. It's exactly this type of application that led me to think more deeply about the types of challenges in natural language processing and the principles that underlie solutions to those types of problems. And I'll start by introducing 3 challenges. First, statistical methods are a bit too shallow for deep language understanding, can make it difficult to figure out what's going on in people's heads, which we saw in the Chinese-English machine translation example. How do you figure out intentions and beliefs of statements through pure number crunching? By contrast, the application of rule-based linguistic principles can often be a bit brittle for large-scale processing and also for adequate domain coverage. So these can fail because it's hard to list out all the applicable rules for various language phenomena across multiple domains. And coupled with these challenges is a lack of explainability amidst the ever-increasing numbers of black box machine learning and deep learning approaches. Yet explainability is essential for supporting the ability for developers and end users to understand what's going on inside of the AI system, just to trust what's going on. And just as a brief aside on this point, many of you have heard of my student Jacob Devlin's work. He's the inventor of BERT. This is a bidirectional encoder that leverages transformers. It has the advantage that it generalizes to many tasks beyond sequence labeling. So that's clearly an enormous breakthrough beyond early deep learning systems. It's also trained but not on human labeled data, another huge win. But I'll note this. Jacob did not have deep learning as his starting point, and that hadn't even arrived on the scene when he was my student. It was sort of the other way around. He became an inventor in that space because he started with detailed knowledge of computational linguistics, and that informed his work in deep learning. And I'll return to that point shortly. So I'm going to make the case that we need hybrid systems, symbolic or linguistic approaches, combined with statistical and machine learning or deep learning approaches to get the best of both worlds. All right. Next, we'll start with challenge 1. So statistical NLP systems require lots of training data. They don't attempt to understand the full context of the sentence. They tend to operate at one word or phrase at a time, the local context, we call it. They use independently trained models. There's no higher order semantic representation, so we can't really sort out the misanalyses and ambiguities, and there's no deeper semantic information like roles of participants in events is not captured. Neural NLP is a huge breakthrough, including transformers and vector-based methods. These operate at the sentence level, and they're not the smaller context, so all models can be trained jointly. This resolves many misanalyses and ambiguities, but they still could benefit from a deeper level of understanding. Both of these approaches require a lot of training data, and the more recent approaches require even more than the older statistical systems. That can be a huge problem for poorly resourced languages. Neither approach takes deeper cross-language generalizations into account. They memorize predicted outputs for given inputs. So incorporating generalizations of some type, both within and across languages, can reduce training data size. It can enable analysis of certain types of constructions that are exceedingly common in language. And we can see this in the machine translation application. So languages require, some of them require spelling out motion and manner explicitly. So in French and Spanish, you would say cross by, I don't know if you can see my mouse, you can't. Cross by swimming versus swim across. So in English, we can just simply say swim across. So this is a well-known phenomenon. It's an example, small example of the types of, a type of generalization for all manner of motion constructions, not just swim and across. And knowing that type of generalization can reduce the need for piles of training data. Okay, so that's challenge 1. Shallowness of statistical techniques, but of course there are pitfalls to purely linguistic approaches, most notably their brittleness. They either undergenerate or overgenerate. That's challenge 2. And the good news is that the availability of large monolingual and parallel text has bolstered the ability to employ statistical machine learning, deep learning methods quite successfully. Now, there are two synergistic perspectives my students have adopted to leverage statistical techniques or machine learning to overcome brittleness of linguistic techniques. The first is statistically filtered symbolic approaches, where in MT, for example, we generate multiple linguistically motivated sentences as the translation output, then we filter statistically, and similarly, in automatic document summarization, we apply linguistic parsing together with something like statistical topic detection to produce a one-sentence summary. Now, these are approaches that have been taken by my students, Dr. Nizar Habash, he's now at NYU Abu Dhabi, and Dr. David Zajic, now at Raytheon. But a second approach is linguistically informed statistical or machine learning, where in machine translation, we incorporate linguistic principles during statistical alignment of the source and target language sentences, and we do that based on parameterized language universals. So that's where the knowledge of language comes in. For example, there's a linguistic principle that says the direct object follows the verb in English, whereas, so we say ate an apple, whereas it precedes the verb in Japanese, apple ate. And approaches like this have been taken by others of my students, including Dr. Najib Fazlayan. He just moved to Facebook, or he just moved from Facebook to LinkedIn 2 months ago, actually, and Dr. Nitin Madnani now at ETS. So we've studied these for multiple languages: Arabic, Chinese, Korean, Hindi, and Spanish are some examples. So summarizing the first two challenges, the lesson learned here is that hybridization is critical for fuller language analysis. And moving into the future of NLP and AI more generally, I think we'll see this more often at different levels of formality. And the key point here is that language is noisy. We require more than just statistics. The community's moved from formal communications to informal and unrestricted media. And also, language is not just about toy examples. We need broad-scale statistics for broader coverage. The community is moving from problems with general characteristics to problems applicable to real-world data, and those two aspects actually feed into how transformer approaches operate. And in recent years, we've seen the first steps toward advanced hybridization, including in modern transformer approaches that leverage deep learning with linguistic insights. For example, the novel cross-attention mechanism that's used to resolve long-distance dependencies. So where two words depend on each other, but one's at the beginning of the sentence and the other's at the end, and maybe in a different language, those are adjacent to each other. So being able to represent that is important. So again, I posit that a strong foundational understanding of underlying constructs relevant to language is critical to being able to generalize in ways that result in these novel breakthroughs. Okay, so that leads to the next major challenge, explainability in NLP solutions, which is somewhat lacking in modern deep learning approaches. Hybridization is an enabling technology for mapping to readable forms, such as logic representations, to provide understandable evidence for why an answer came out the way it did, whereas vector-based methods provide a bunch of very long feature vectors of numbers, and those might be really hard to interpret. Okay, so explainable frameworks have begun to emerge. For example, in text classification, labels are explained through, for example, visualization tools, highlighting the input words to indicate salience. But wouldn't it be nice if we could produce a more readable explanation like the one shown here? For our earlier translation example, everyone can guess in their hearts includes correct pronoun usage of their and correct object placement of hearts with a higher probability of correctness. 0.8. This is a little stilted, but it's giving you some probabilities and saying a little bit more about it. So lower probability for everyone heart and can guess. And again, hybridization is important here. The first part of the explanation where we're talking about linguistic structure, correct pronoun usage, for example, and the second part to statistical computation, the probability of correctness. But still, I see this as just scratching the surface for what's needed for explainability. So what additional linguistic knowledge is needed to support explainability and for what applications? And that's where my research is really headed now. We want to explore linguistic annotations to infer deeper knowledge. And this table shows two columns. The first column is first-order knowledge. It refers to annotation with linguistic labels, essentially. For example, mood distinguishes guess from can guess, which is permissive, or must guess, which is obligative, or might guess, which is labeled possible. So that's the top row. And then dialogue acts, shown here to distinguish can you do from something like did why happen. So one of those is sort of a request, and the other one is requesting information. But there's more than just annotating with linguistic labels. So that's column one. The higher order, or second order knowledge, is about what we can infer beyond those labels. From confidence values, taking mood labels on the left side, you can infer a probabilistic belief that X may or may not have happened, for example. Similarly, intentions, relationships, beliefs, these can be inferred from dialogue act, and you can see that in the lower right quadrant there. You can infer from dialogue acts what these relationships are, that you have superior subordinate relationships, for example, and that the intended activity, what it is, and its associated beliefs for reported actions. So now back to our earlier application in the cyber NLP field. We're going to see that I'm appealing to what I mentioned as a major theme, addressing explainability. To do this, we're building on lessons from machine translation and language analysis, where hybrid approaches have been shown to be efficient and effective. And these are critical for more now than ever before, where the world has moved to informal communication and social media. So that's the starting point for our social engineering ask detection system. With my students, Brody Mather and Adam Dalton, and I provided a citation at the bottom of the slide, and there's nothing in the middle yet, don't worry, I'll bring it up. I've adopted hybrid approaches to handling informal language, and especially implicitly conveyed information that you don't necessarily see on the surface. So what does that look like? I gave a hint earlier. A social engineer might say, check out this great offer. Our ask detection system figures out that the ask is to click a link. Now this is a propositional representation, and it's keying off of particular triggers. The framing, remember I mentioned that each one of these is coupled generally with a framing, is posed by the social engineer to the potential victim as a gain. So the social engineer wants the potential victim to think they have a chance of getting a great offer. And sometimes the framing is a lose. You'll lose if you don't click the link here. You lose something. You lose access to your resources, whatever. So the framing can be a gain or it can be a lose. Where am I headed with this? The intention behind this is access to credentials or funds. And this is really the next step of explainable AI. It's not really implemented yet, but it would be great if we could say the intention to gain access to credentials or funds per request to click on a link associated with finance money. So this is giving the why. Why do we think this might be the intention? All right, and we know some features associated with the things that they're clicking on. So that's really where I'm headed. We already have implemented the blue and purplish. It does show up as purple, blue and purple, the top two, ask and framing. We've implemented those representations, the ask and the framing. These are actually derived from generalized linguistic principles. So now the next step is to be able to generate the type of explanation that you can see there in the italicized blue. And I don't think this is the type of output you expect to see with strictly neural net systems, not yet, but I think we could get there if we take these as primitives and compose them. So before embarking on the development of an NLP agent to help with this problem, I and some colleagues, Larry Bunch and Tomek Strauss-Lukowski, we undertook an exploration of possible sociolinguistic factors to be taken into account well beyond statistical and neural machinery. So social engineering is so prevalent, we are easily able to latch onto a real-life example. And this is one where we actually played along for several weeks. They look like chat or text or something, but these were actual emails. They were very short emails, but it went on for a while. So the communication starts with some lightweight conversational questions by the social engineer who is posing as the dean of the college. Are you available? Sorry for disturbing. I want you to help with something. Those are probably canned. Meanwhile, the potential victim, that's our team, we're pretending to be the PV, all right? We respond sort of non-committally. What's up? Okay, what is it? And also confirming deception with the question, everything okay with the project? The social engineer, SE, reveals what we call the ask, the demand, which is to buy a bunch of gift cards. 5 $100 gift cards to be exact, and interestingly, they want actual physical cards. The specific request is noted by our team, this thing about physical cards, and we bring it up later. At this point, we pause for a whole week, and this is the part I found the most fascinating. The social engineer, I think there's really a human at this point. Social engineer gets impatient. They don't for one moment suspect that the PV is onto them. They imagine that their authoritative role is compelling the PV to proceed, and then they're just very comfortable with being aggressive. Are you still there with me? I really need that card to send it to a friend of mine, okay? Finally, the PV, our team, responds. We hatched a plan that we're now going to implement unbeknownst to the social engineer. We correspond back and forth. Each exchange, though short, again, is separated by sometimes a week-long lapse. Hey, still want these cards? SE, yes. Have you get it? And we don't correct typos. Those are real. They're indicative of an attack, actually. PV, sure where to send them. SE, send them here for me. Attach it with massage here, okay? SE, just scratch it and take a picture of them and attach it to the email. Tend it to me here, okay? PV, you said you needed physical cards. This is referring back to that prior exchange. Need your mailing address to send those. Send it for me here now, okay? And then we continue stalling. So where's here? Your home address? SE, I mean here, not my house. Just take pictures of each of them and send it, okay? So you're getting the idea. As this story unfolds, we're seeing that the social engineer is getting more and more impatient. They're demanding that the PV send an image of the card over email, for example. So more time goes by. A few days later, I don't think this is the actual image we sent, but anyway, we found this, used up card on the web and we posted it, but we're pretending this is it just for this presentation. We did send this image, or at least we claimed it was an image, and it's a fake gift card. So the social engineer gets very aggressive and their grammaticality plummets. They demand that the PV send an image of the scratched off code on the back, fast, and that word fast shows up. You could see it bold-faced in the bottom there. It shows up a whole bunch of times on the next slide. So there's no holding back. The SE continues to act like an authoritative superior. Another week passes. The SE pushes again, demanding that the card be sent fast. The PV stalls, or citing security concerns. Finally, we did send an image of the back of a card partially scratched off, and the SE brusquely complains that the code is not scratched off well enough and that the PV only sent 1 card instead of 5 cards, and yada, yada, yada. So there's an interesting psychological phenomenon here. This is real, right? So the socio-behavioral context is one where the SE is impersonating someone whom the PV would regard as a higher up, right? That's critical. That's what's causing this dynamic to happen, a dean in this case. So the SE counts on the authority effect, and I was astounded that the attacker is not prepared for counter-deception. This led me to believe, yeah, we probably could waste their time. What if you had a bunch of bots wasting their time? Anyway, so we could have actually taken this further, could have, if they clicked, there are other things we could have done, but I won't go into that. So our main point, we were in a program where we were asked to unveil the attacker, for example. Our main point was to show that it's possible to keep an interaction going for quite a long time. And setting up a bot to do this would be probably on a grand scale would be a good thing, probably help with this problem in significant ways. So drilling down, we've implemented a chatbot to do this automatically. Our starting point was to notice that each interaction with the social engineer has some form of explicit or implicit demand, the ask. I want 5 gift cards, for example. And we identified 2 types of asks just to simplify initially, so we call it either a give or perform. So you're trying to get something out of you, and you're going to give it, triggered by words like want. The amount I want is 5 $100 gift cards. The second is perform, triggered by the word, in this case, contact associated with a clickable link. And so figuring out what kind of ask is being employed? That was our first step. And we've coupled that with framing detection. I mentioned the two come together, not always, but most of the time. And here you're determining the risk or reward that the PV perceives to be associated with the SE's ask if they were to be who they say they are. You know, what would your risk or reward be? Like if this were the dean and you're going to get fired, that kind of thing. So the first is the risk, that's a lose. So in this case, you know, don't miss this rebate offer of 20%. So maybe you're going to, this one isn't sent by the dean, that particular one. The second is a gain triggered by the word get. You could get up to a 20% discount, all right? So I threw a few examples together here, but it shows you the give, the perform, the lose, and the gain. That's what we pivoted off of. And now we're back to the overarching example with the same acronyms, SE and PV, as mentioned earlier. And coupled, the ask and the framing coupled with information about the structure of what email, you have to know the medium that you're working in, so there's a little bit of structural information, allows us to produce an NLP response. So recapping, did you know that you may be able to get up to 20% discount? That's the framing. That's followed by, and so we produce a framing that looks like this. So it's a logical representation, followed by click here to check your eligibility. That's the ask. And then we leverage those two inputs to produce an NLP response. So based on check eligibility, good to know, how do I get the process, go about the process of checking eligibility. So this is kind of what I talked about before. So the next response is really about time wasting, websites not opening, and finally active defense, implementing, actually sending a link that isn't the one that they sent and attempting to covertly verify the attacker's identity, essentially. So wouldn't it be nice if we had a bot inside? I wouldn't want a bot to replace humans, but what if it were just sitting there flagging these emails and suggesting responses like this, or even finding a way to identify information about the attacker. For qualitative results, let's look at some examples. The central goal here is to detect and thwart attacks, but we're wasting time by playing along as a part of the greater good, keeping them from harming lots and lots of people. So consider the 3 attack emails. They're shown in the first column of this table. These are just different ones, and we're going to focus really on the last 3 columns, but the first 3 columns are the email input, the ask and the framing, and then we applied kind of a baseline thesaurus response, which sounded really canned, things like how are you, thanks, what should I do now? The system really doesn't understand much about what the social engineer actually said in that case. By contrast, the same emails yield a more responsive output when we introduce symbolic and linguistic principles, things like too good to be true, what should I do now, or the website doesn't open, is this the link? And these are time-wasting techniques. That's the second column, the initial AI response. And they go beyond the canned responses. But the best responses are in that very last column, where we improve the responder to understand more about the structure and semantics of the social engineer's input rather than just parroting back Eliza style. So, and that's something that's not possible in a strictly neural paradigm, although there's certainly, if you have enough training data, there are certainly things you can do with that. It's a question of training data in this type of, in this context, you have enough training data for that type of thing. The responses use the same time-wasting tactics, but they introduce phrases that make reference to content in the original email. For example, in the first email, the social engineer asked the potential victim to make contact. So the response is, I will make contact as soon as possible. The third email down at the bottom, the lower right-hand side, here the potential victim the email requests that the potential victim check eligibility by pasting a link. So the adaptive response is, thanks, but we need more information before I paste the link. So our system's getting better and better as we move rightward through this table, and in fact there's more recent results showing additional improvement in response generation through machine-learned self-attention BERT-style models, but we are interested in further hybridizing this to make sure it's explainable. Let's move to the next one. As it turns out, adaptation of this approach to new domains and tasks is more straightforward than one might imagine, because we have these ontological categories, lose and gain, and we can refine those depending on what the domain is. So 3 of the domains here, we've actually deployed the social engineering asset detection system as a part of a DARPA program. We've demonstrated similar, so we were looking at attitudes toward non-pharmaceutical interventions in COVID-19, and we developed something called stance detection, which is based on that same idea of building out on a couple of important ontological categories and building these propositional representations. So it's, do people's COVID-19 attitudes predict how they will behave with respect to COVID-19? Whereas the last one is more in the future, where we're headed next with foreign influence detection. Can people's attitudes be used to create targeted influence, for example? Stance detection, by the way, computes attitudes toward a particular thing, in this case, mask wearing, social distancing, and it's different from standard statistical sentiment detection. I'll get back to that in a moment. Here you can see an online conversation among Jan, John, and Tim. It's kind of small, but they're basically talking about masks and, whether, sort of they're against masks. So what makes this different from mask detection is that we've added what's called a belief, believing that the mask protects you, or believing that it's going to cause CO2 poisoning, it's going to make you ill. That's what those 2 propositional representations are there. And so when we build stance, it's a sentiment with respect to a particular belief. So if you feed a sentence into standard Allen NLP, it'll give you one sentiment answer. But this one's saying part of that sentence has this stance, and it's toward specifically masks and that they're going to make you sick, and the other one is toward whatever the other thing is. So it's not always that one sentence has one sentiment. And what's interesting is we're able to borrow these same notions of lose and gain as a part of the framing and extend them in this domain as well. And we end up with those readable representations. And again, what we'd like is to express an intention and explanation as we move into explainable AI. So this here, against this these statements illustrate that the group is against mask wearing, given beliefs that masks are non-protective, they cause illness, CO2 poisoning, they're restrictive, and we would gain freedom if we were not wearing a mask. So that's what that conversation is about, sort of an analysis at a propositional level. And I really think it's the next step for explainable NLP to do things like that. And I mentioned sentiment detection, and I think I can go quickly over this, but there's quite a quantitative and qualitative distinction between stance detection and sentiment analysis. So if you say, I don't like not wearing masks, Allen NLP says you have a negative sentiment toward masks, whereas and by the way, the double, triple, we've come up with quadruple negatives, and it gets really complex. So having this propositional representation does, as a byproduct, address some of that. So here, the stance representation is that wearing a mask there's a positive attitude. It's not fully positive. It's 2.75, not 3. Because of this convoluted. The more you add in this modality, it's called hedging. You're sort of pulling back from the position. Well, I don't like not wearing masks. It's not like I'm demanding to wear a mask, right? So maybe there's something pulling back from that stance there. The other thing that stance handles that sentiment doesn't is just the thing that I said before. The governor required mask wearing. Well, you might have 2 different stances if somebody makes that utterance. They're saying that they're not really, they could be on the, it could be that they're trying to say, wow, this really stinks, we're being restricted, or it could be they're saying, wow, this is great because we're protected. So that's what those 2 stances mean there. Okay, but more importantly, explainability, right? Stance detection provides a foundation, just like ask detection is. And I just wanted to show you one example of moving to different types of tasks and problems to show the flexibility that when you have this propositional representation embedded, and what I hope will soon be embedded in deep learning approaches, you get some explainability. So where am I headed next? I'm looking at stance detection for example, in a project called, and actually this slide has changed, but cross-cultural negotiations is one of the areas I'm interested in, but there's also mediation project called Civil Sanctuary, which just became a project this past year, where we're using stances to consider when to have a bot sit there and perhaps soften, when there's a debate, say on Reddit or whatever, soften the way people are saying things, not blot out what they're saying, allow people to have their say, but to say, did you mean this, and rephrase it in a way that is considered, quote, civil, all right, within Civil Sanctuary. I also mentioned that hybridization for explainability is underway. It's not yet implemented. We're working on that right now. And then another area is multiple modalities, bringing AI, vision, NLP all together, speech, fusing lots of different inputs can help for explainable AI. Humans are able to figure out what went wrong in an interaction. They can see your gestures, they can see your body language, they can hear you, they can hear the intonation. So computers really need to catch up. And then obviously it's always, in my humble opinion, good to do all of these things in multiple languages. So that's it. Thank you. Questions? Questions? Yes, you. Oh, there's one there and one there. Let's start there.
I was wondering, as the examples you gave of attackers look like they were humans behind those messages, does those become motivated themselves? How would that take?
Yes. So this is one of the. Okay. So the question was, a human was behind the example I gave, and what happens? I think the shortcut way of saying is, what about ChatGPT? Is that what? Yeah, and so there's something interesting, a question I have in there, which is, since our whole goal was to kind of sap resources, to keep that from happening, kind of like blow it out of the water, it's just a question of whether you can perhaps sap whatever that resource is that's producing the automation. I don't know. I don't know the answer to that. I suspect people would find a way to get around that. These are definitely challenges that I think we face in the future. So, yes?
I had a question on your piece earlier where you were doing kind of an analysis or ranking of sentiment. Has that been applied to things like news articles, things that people forward to each other in a network or something like that, to see if there's an increase in inflammatory language or clear biases in articles? So people are really trying to look for neutral news or neutral messaging. Is there a way that type of analysis is applied to entire articles or entire sets of text as opposed to individual or small pieces?
Oh, okay. So I think the question is, can this analysis be applied to larger inputs like articles and news and things like that? By the way, we have applied it to both of those. Or is it mostly smaller snippet, dialogic in nature, that kind of thing? Okay. Yeah, we've actually applied it to both. I almost didn't see the point with technical article, I guess for detecting bias, I think that's a really good one. But we found this other reason we have to do it for more formal documents, which is there's another project I'm just starting on where we're looking at just what general population of interest. What are people interested in? What sort of articles are they reading? And where are people gravitating toward? Just to get a feel for what their interest is and maybe what the stance is with respect to that interest, although they may not have that stance, but they're perhaps it could be biased and maybe they're just interested in what it's saying. I don't know. But I think for detection of bias, that is another possible application for this. And detecting bias is really critical really critical for so many reasons, particularly with things like ChatGPT, but even resources that people use to do training, to build their systems otherwise for any kind of task. The ACL, Association for Computational Linguistics, they ask people to make a statement about bias and what the data set is, and what mitigation techniques have you applied to get around that. And I think it would indeed be important to be thinking about ways to do that, and stance could be one of them. And we have to worry about this more and more, definitely. I don't know if I fully answered your question. Okay, yes, over there.
So for the COVID example, you were considering sentiment analysis. Is there any comparisons that you can do with respect to this new software, LIWC, which does sentiment analysis?
Wait, is there any, can you say that very last?
Did you compare with LIWC, the sentiment analysis?
LIWC? Oh, yeah. Oh, okay. Yes, got it. No, we did not. No, I know what it is, but nope, we didn't do that. We did this with Allen NLP using the most recent model at that time, so it was like a week old or something, and people were actively, I brought that into my classroom recently though, and I noticed it changed again. Like, we tried some of the same examples from last year and they were getting different answers. So I think that one is heavily used enough that I felt confident, it's a community standard. But yeah, there's certainly others out there, and that's a good one to compare to see what happens. But we haven't done it. Yes?
On the subject of the stance detection, it seems, if I understood correctly, that it relies on extracting some aspects of propositional representation from text. As you mentioned in the beginning of the talk, doing that sort of analysis tends to be brittle and specific, the rule-based, propositional-based. What do you do to make that general enough to be able to fit together?
Yeah, so what we do is the algorithm itself is portable almost entirely for doing stance detection, ask detection, all of these, but the resource that it draws from changes depending on the domain or the task, and that part of the process of domain resource building is automated and brings in some machine learning techniques as well, but typically is human in the loop, and it takes about 2 hours. So that slide where I showed all the different applications takes about every time we switch to another domain or task, it takes about 2 hours of a human in the loop after we run a system that does automatic analysis of like a big swath of data and produces predicate argument pairs automatically, and then kind of categorizes them a certain way so a human can quickly go through them, and then those get added to the lexicon. Then we run and see what happens. So that is a trade-off, because we have to deal with that 2.5 hours, but we're not dealing with days of human annotation, at least. There's some things we don't do, which is good, and then there are other things where we do have that trade-off. We have to have the 2.5 hours or whatever it is. Yeah, we're happy. We've done this, we've had students help with it, on a Sunday, and then by Monday we've got a system because it plugs right in. We don't have to do all that training overnight or anything. But there is that automatic process of learning what the predicate argument structures are, and that part helps us to build the resource much more quickly. I like the idea of that, by the way. I like the idea that I think we can tell a customer, like, all you need to do is run this thing on whatever your data is, I don't know what it is, and it will suggest things to your users, and then they have to do this additional step. We have an interface we develop where they can quickly bin, and then it becomes the lexicon, and then they can run it, and they're pretty happy. Yes? Okay, wait. Do these models adapt to false positives or detect false positives? To have a false positive, you have to have a ground truth. And I would say that's outside of the realm of the algorithm itself. The algorithm needs to be evaluated on ground truth by an evaluator as a separate step to determine how well it's doing. And in fact, we had many different forms of evaluation that DARPA used. For example, they had a human who was we did a little bit like a Turing test, which is flawed, but in that particular program, it was like a Turing test. So where they were corresponding. They didn't know which thing was machine. They asked us to respond as humans too, which I also feel is a little flawed because we're the developers of the system. We can, there were lots of problems, but so they had to grade it on things like fluency and, was it relevant? Were these responses making sense? Did your system hang? That was always a bad thing. But they were actually corresponding and trying to guess which one was the machine as one part, and the other part was knowing that it's a machine, a different set of evaluators, obviously. How well is it? Is it interacting well? How many turns did we get out of it? We also had a capture the flag thing where it was, we were supposed to, as we responded, be pulling out things from what the social engineer said and populating like a table with the various pieces of information for unveiling the identity of the attacker. So there are many different levels, but yeah, so it's hard to say what's a false is it a false positive if you respond a certain way and it misses the mark? I mean, a human could say that's not really a relevant response, but I don't know is it a false negative, is it a false, I don't know, it's hard to call it that. But I think it's a good question because it brings in evaluation and how do you determine that you did your job? How do you know you're done? Did you have success? Those are important questions to ask. Yes? Wait, I think I need to come a little closer. Or unless somebody can relay the question to me.
As we all know that ChatGPT and GPT-3 are very powerful and I'm curious, is it still necessary to have this ability since we have such a powerful
Really, almost next to impossible because there's an engine, a motor, or something out there. The subway.
It's a train going through.
Yeah.
Okay. You also mentioned that ChatGPT and the GPT-3 are very powerful language models, right? And I'm curious, is it still necessary to have this ability? And since we already have large language models, how can we have how can they help this ability? And yeah, maybe we could give some comment.
Can ChatGPT help? Is that what you're? Oh, okay.
Yeah, help is ability, or is it still necessary to have this ability since they are so powerful?
I think his question is, since this language model is so powerful,
Yeah.
and it's necessary to have this capability, and how this language model can help this capability. I think that's what he's asking.
So I hope that, this is an old slide deck I have. Do you mind if I, hold on a second. Is there a way to black out the screen? Oh, it doesn't matter. Doesn't matter. Let me bring up, I'm going to answer your question. One moment. Thank you. I was noticing halfway through the talk I had an old deck, by the way. Okay. One moment. So, I want to talk about ChatGPT for a second. And that's probably one of the most frequent questions that I get nowadays. Didn't ChatGPT already solve this? So we've seen a lot of news, right? We've recently, for example, last month, Stack Overflow banned ChatGPT generated posts. Problem is that there's no explainability in these, so when it produces those wrong answers, there's no way to look inside the system and figure out that it's wrong. And the question is, should you trust it? And maybe you should double check it, but then what's the methodology for double checking? And that's a lot of overhead. And so that's just something to be careful about, that I do believe that we should use pre-trained generalized tools for tasks like question answering, but then fine-tune with propositional analysis. In the social engineering case that we've been looking at, finding a propositional representation helps us to determine what happened inside the machine, makes them explainable. So trustworthy computing is like a big target area right now, right? You need to be able to trust what that output is. So I just wanted to put that out there. Also, for answering, I played around with it. We all have, what's the incidence of cancer near power lines? ChatGPT does a pretty reasonable job for this one, ultimately reaching the conclusion that results are mixed with no clear indications of an increased risk of cancer. So you would think that's pretty good, but this is exactly where hybridization and explainability are essential. So whether you get a correct answer or not, you want to know how it got to the answer. And then incorrect answers can run rampant. And we've all seen these. I've seen them very recently. And I was thinking, I was talking to Kay, I don't know if you're in the, oh yeah, just that I was talking to a doctor recently and asking, should I take B12? And he said, it can't hurt. So here's my thought. I want like, and he did give a dosage, by the way. He's like, can't hurt. Okay, here's the dosage. But I thought to myself, can't hurt, which are two negative things, which kind of makes it a positive, but a hedging positive, right? In my world, I'm like doing all this NLP while he's talking, and then I forgot to, I had to ask him again what the dose was. But if I had the components of a propositional representation being built as his neurological process is going on in his head, and he's popping out that answer, it can't hurt, to my question. And if it could take those primitives and compose them in a way, and at the end, I would get this really good answer for why he's skeptical, because maybe some articles say, well, there's a very weak correlation with positive outcomes using B12, and that this is all going through his head. I would love to have that as a part of the answer, not just the answer. So that's my shtick on, did I say all of that down here? Oh, yeah, all the stuff I said. Also, there was an article in December, essay writing for movie analysis, where it misses up, this is for Ferris Bueller's Day Off, it mixes up the sidekick with the main character. So there are just these things where, and that was, I guess, for somebody who went in and tried to go back to high school and do an AP class in English, where they had to draw parallels between Ferris Bueller's Day Off and this other very ancient text. And thought that was interesting that they were, and I think she got like a C, I'm not sure. So we're not there yet. We're not at the point where it's solved and that we already have all the good answers and everything we need. And also, even if we did, I still want to know why my doctor said it can't hurt. I should ask him someday. But I mean, he's going to be like, here are all the technical articles, the pro side, here are all the technical articles. I just want that simple explanation of what's going on. So. And I think when you're writing your systems and an answer pops out, you're like, wait, I got to figure out where the bug is. Wouldn't it be nice if you had a little bit of help for where you might look first? So those are my thoughts. Yeah?
During your research of sensitivity analysis, have you come across logic regression and name-based? If so, which one you have used to talk about this?
Have I come across what? I can't hear. Okay, say the name again. Name base. Oh, naive Bayes. Okay, sorry. I'm not parsing very well. Okay. Yeah. There are a lot of different, so sentiment analysis has been around for, I don't know, 20, 30 years maybe. So there are, I would say, I don't know what the paper count is in ACL nowadays, but I know it's in the thousands. So yes, these Yeah, there are many, many different approaches. Again, I was sort of picking something that was a community standard that I'm seeing, but I mean, it's changing so rapidly, the community standard tomorrow could be very different. So I was just going by a BERT-based model of sentiment analysis and comparing that to stance detection. And the BERT-based model was, it had been trained like the week before, so it was pretty recent. But thank you for bringing that up. There are lots of different approaches to any classification task. A lot of different, there's just so many out there, you know, RNN and DNN, all of the different approaches. So. Yes?
I have a question about the slides where you show the covering stance. I'm curious, where do you get those constants like game freedom? Because the sentences doesn't show anything about freedom.
Yeah. Good question. So the categories of belief, they're usually small, under 20, and those are what come out of the semi-automatic process that the lexicon builder uses. When we present all the predicate argument structures in a particular, we sort of group them together, they cluster together, and they walk through them, they come up with those belief categories. You are really astute in noticing that. So we had protect, restrict, we had a whole bunch of them, depending on the domain. Those are the buckets that get used for the lexicon resource that we build. And then we run it, and it pretty much produces, in each domain, it produces these stances for, I don't know, maybe half of the sentences. So it's pretty good. I mean, through redundancy and also synonymy, you're going to get a lot more out of this as well. So really good question.
Thank you, Denise. We have time for just one more question.
Okay, I'll actually, in the interest of time, I'll wander up and ask you.
Okay, cool. Thank you so much.
There'll be time to meet the speaker at about, I believe, 3:30 for students. Thank you very much.
Thank you. Thank you. Really good questions.